Hello, my name is Kissos from Ben-Gurion University. This is a joint work with Niv Gilboa named Prune+PlumTree Finding Eviction Sets at Scale. Eviction set is a collection of memory addresses that fill a single cache set. At the left-hand side, you can see the RAM memory, whereas on the right-hand side, you can see the cache memory. You can think about the cache memory as a table with S rows and W columns, each row named cache set. The objective is to find a minimal eviction set. That is, we need to find exactly W memory addresses from the RAM memory, that all of those addresses maps to the same cache set. In that example, it's cache set number 2. Finding eviction sets is essential for prime-and-probe attacks, which its goal is to learn sensitive data or patterns of a victim process. Eviction sets allow an attacker to infer the residence of a memory line in the cache. Cache side channels are powerful, robust, and easy to use. Many attacks are based on cache side channels, such as Meltdown by Leap et al. And Spectre by Coucher et al., which leverages speculative execution to access protected memory regions. Foreshadow by Balk et al. Also exploits speculative execution to extract sensitive information from Intel SGX enclaves. Extracting cryptographic keys by Liu et al., leaking information on user input by Schwarz et al., de-randomizing ASLR by Ung et al., spying on browsing activity by Oren et al., detecting co-residency in cloud environments by Zhang et al., and creating fast cross-core cover channels by Maurice et al. The existing algorithms determine an eviction set for a given target address. The baseline eviction set algorithm by Liu et al. Runs in S squared W squared time complexity, where S is the number of cache sets and W is the associativity of the cache. That runtime is quadratic in the size of the cache. The group elimination algorithm by Villa, Koff, and Morales, and another work by Ramkrishnan, Zai, Mashamant, and Yu reduced that time complexity to S W third. That a significant improvement over previous work, since S is much larger than W. The improved group elimination algorithm by Song and Liu and the hierarchy-based algorithm by Prune+, Turan, and Verbawad, and another work by Gyu, Shin, Chang, and Yang reduced the time complexity to S W squared. Finally, the most recent algorithm, the prime-prune-probe by Prune+, Giner, Gruss, and Verbawad, reduced the time complexity to SW, which is a linear time in the size of the cache. All the previous mentioned algorithms find a single eviction set. However, some attacks naturally require the use of multiple eviction sets, such as template attack that monitor multiple cache sets, and Spectre variants that translate a byte of memory into one of 256 cache sets. But even when monitoring a single cache set, finding that specific cache set is non-trivial. The attacker has to find a specific cache set with a pattern activity. Therefore, the attacker has to find most of the eviction sets in the cache and test each eviction set to that specific pattern. The current approach for finding all eviction sets in the cache is to find a single eviction set and then repeat that process at least S times. The time complexity of that approach is at least SW, which is the time complexity of finding a single eviction set, times S, which is the repetition. Our first contribution is the introduction of Prune+PlumTree algorithm for finding S eviction sets in time complexity of SW log S, under the assumption of least recently used replacement policy. The next contribution is the implementation of the Prune+PlumTree algorithm for mapping A3 cache of Intel CPUs from 8, 9, and 10 generation in roughly 40 milliseconds, outperforming the state-of-the-art by 2 to 3 orders of magnitude. The next contribution is a variant of the Prune+PlumTree algorithm for random replacement policy policy with time complexity of SW² log S. The final contribution is a proof that Prune+PlumTree algorithm runtime is asymptotically tight for least recently used replacement policy. We are all familiar with the cache memory. It has set associative architecture. The cache is divided into S sets and W ways. A memory line is mapped to a specific set, but can be stored in any way. Insertion of a memory address to a full cache set leads to an eviction of a resident line. The eviction is determined by the replacement policy. The timing differences between a cache hit and a cache miss creates a side channel. The prime and probe attack uses that timing differences. First, the attacker prime his eviction set to a specific cache set. As a consequence, the cache set is occupied by the attacker memory addresses. Next, a victim makes some calculation that uses that specific cache set. As a consequence, the victim evicts some of the attacker memory addresses. Next, the attacker accesses his eviction set and measures the time access. If the time access was fast, he receives cache hit, and if the access time was slow, he can conclude that he received cache miss. Hence, he can infer that the victim used his own cache set. Now, I'm going to explain about the prime, prune, and probe algorithm, which announced in 2021 by Prune et al. We will use some of the algorithm concepts in the next few slides. The goal of the algorithm is to find a single eviction set for a given target address Z. The first phase is to collect a pool of random addresses. Next, we prime the pool of addresses into the cache. Some of the addresses stored inside the cache, and some of the addresses remained in the RAM memory due to lack of space. Next, we make the prune stage, which we traverse the pool again and discard all the addresses that experienced a cache miss. That is, we discard all the addresses Q, R, and S. So we're left with all the green addresses. All of those addresses can be stored in the cache simultaneously. The algorithm assumes the least recently used replacement policy. So in the left-hand side is the least recently used place, whereas in the right-hand side is the most recently used place. So suppose we have a target address Z, and the target address Z maps to cache set number 3. Next, we prime the target address Z into the cache. The insertion of Z into the cache enforces the eviction of address H outside the cache, since H was located in the least recently used place. Next, we probe the pool of addresses again. All of the addresses in the green, which is all the addresses of cache set 0, 1, and 2, experience a cache hit, where all the addresses of cache set 3 experience a cache miss. Then, we collect all the addresses that experienced a cache miss and declare them as an eviction set. So, our algorithm, Prune+PlumTree. For any coverage between 0 and 1 and epsilon value greater than 0, the algorithm returns n distinct and random eviction sets such that n divided by s, which is the number of cache sets, is larger or equal to the coverage value, with probability larger than 1 minus epsilon. The algorithm has two stages. The first one is the prune stage, which obtains a union of minimal eviction sets. We call that set C. Next, the PlumTree stage, which divides the set C to n distinct minimal eviction sets. So first is the prune stage, which we sample SW random memory addresses. We refer that set as a candidates. We prune the candidate set as in the prime prune and probe algorithm. Observation: the prune candidates form a union of minimal eviction sets. Next is the PlumTree stage, which its goal is to separate each eviction set from the union of the eviction sets. We sample S random memory addresses and refer that set as the representatives. We inductively divide the union of eviction sets into two smaller unions of eviction sets. For that purpose, we use a binary tree. The idea behind the plum tree is to start at the root of the tree with the candidate set, which is a union of minimal eviction set. In that example, we have 4 eviction sets, such that each color and shape represent different eviction set. The representatives group has at least one address that corresponds to each eviction set. The idea is to divide the candidates and the representatives into 2 halves, such that each half corresponds to each other. Each node of the tree, the left one and the right one, has its own candidates and representatives group, such that the 2 groups match each other. Next, we continue to divide each node until we reach a leaf. A leaf in the tree represents an eviction set. To show a run demo of the plum tree stage, we first need to understand the LRU thrashing property. Suppose we have the addresses A, G, L, and C, and all of those addresses maps to the same cache set. Suppose we have another address, Z, that also maps to that specific cache set. When we prime that address Z into the cache, the insertion of Z to the cache enforces the eviction of A from the cache. Next, when we test the addresses A, G, L, and C, we receive a cache miss on address A, since it was evicted by address Z. But also, when we access address A, we evict address G from the cache. Next, when we test address G, we receive a cache miss, since it was evicted by address A. But also, when we access address G, we evict address L. And so on, we receive a cache misses on addresses L and C. In one traversing on addresses A, G, L, and C, we receive 4 cache misses. So now I show a run demo of the plum tree stage. First, we prime the candidates into the cache. Suppose we have the representative set W, X, Y, and Z. We take half of the representatives, for example, W and Z, and prime those addresses into the cache. The insertion of W and Z to the cache enforces the eviction of A and H outside the cache. Next, we test the candidates. When testing the candidates, we receive cache misses and cache hits. All of the addresses that belong to cache set 0 and 3 receive a cache miss. We take all the cache misses and put on the left node. Next, we take all the cache hits that belong to cache set 1 and 2 and put on the right node. Each node have its own candidates and representative sets, that the candidates and the representative sets correspond to each other. Next, we continue to divide each node, the left node and the right node, until we reach a leaf. A leaf in the tree is an eviction set. In that example, we have 4 eviction sets. Now, we would like to adapt and implement our Prune+PlumTree algorithm to run on modern Intel CPUs. The Intel replacement policy studied in the literature. It has complex version of quad LRU, non-deterministic, and leader and follower sets. Intel CPUs have 2 replacement policies. The first one is more susceptible to LRU thrashing, whereas the second one is more thrash resistant. The leader sets employ a constant replacement policy, which is more susceptible to LRU thrashing. The CPU chooses between the two, according to the miss rate on the leader sets. So the two main challenges are the more complex replacement policy and system and measurement errors. We overcome those challenges by applying patterns to manipulate the replacement policy and a repetition on the prune and the plum tree stages to eliminate error measurements and noise. We repeat the prune several times and the plum tree several times. That is, instead of building only just one tree, we build several trees. Now, we evaluate our algorithm, Prune+PlumTree, against two state-of-the-art algorithms, the group elimination algorithm and the hierarchy-based algorithm. We make a comparison on L3 cache of 3 Intel CPUs from 8, 9, and 10 generations. We refer a pageheads as an eviction set consists of addresses starting at offset 0 within a memory page. In Intel CPUs, we can interpolate 64 distinct eviction sets from a single paged eviction set. So in that comparison, we map only the paged eviction sets, and then from each paged eviction set, we interpolate 64 distinct eviction sets to receive the full mapping. Our algorithm, Prune+PlumTree, succeeded to map more than 98% of the cache in a runtime of 40 to 60 milliseconds, which is roughly 2 orders of magnitude faster than the state-of-the-art. In the table below, we can see the runtime of the group elimination algorithm, which is 25, 53, and 71 seconds, whereas the hierarchy-based improved that runtime to 7, 10, and 48 seconds. However, our algorithm runs in 40 to 60 milliseconds. Now, we would like to push even further. Recent suggestions suggest a random cache, which has uniform distribution of addresses to cache sets. In that configuration, each eviction set must be discovered independently. So, we make an experiment on Intel CPU from 9th generation, which has more than 16,000 cache sets. In the plot, in the bottom and in the up, the x-axis is time in seconds, whereas the y-axis is the mapping coverage. Each dot in the plot is one plum tree. The red dots describe the process of finding paged eviction sets. As we can see, after 5 plum trees and 40 milliseconds, the algorithm succeeded to map almost 100% of the eviction sets. The blue dots describe the process of finding all eviction sets independently. As we can see, the Prune+PlumTree algorithm succeeded to map almost 100% of the eviction sets after 7 seconds. To put that in the context, the state-of-the-art algorithm mapped 256 eviction sets in approximately 11 seconds, whereas our algorithm mapped more than 16,000 eviction sets in approximately 7 seconds. To conclude, we show the Prune+PlumTree algorithm that finds any constant function of the cache in time complexity of SW log S. We show an implementation of the algorithm on 3 Intel CPUs from 8, 9, and 10 generation with a runtime of 40 to 60 milliseconds that outperforms the state-of-the-art by 2 to 3 orders of magnitude. In the paper, we show a variant of the algorithm to random replacement policy with time complexity of SW² log S. Also, we show in the paper that the Prune+PlumTree runtime is asymptotically tight. Thank you.